Today's lesson is about complex numbers and the fundamental theorem of algebra. It really has to do with writing polynomials, giving their roots, and how to find their roots. Okay, so it starts out with a quick review. Complex numbers mean they have an I in them. They're imaginary. You have the real part is A, the imaginary part is the I. You add your real parts together, so 2 and 4 gives you 6. You add your imaginary, 3i minus 7i is negative 4i. That's all there is to it. If you subtract, you do the same thing. 1 minus 5 is negative 4. Negative 3 minus a negative 2 is negative I. Multiplying, you FOIL. So I'm going to multiply here, and you get 2 minus 8i plus 3i minus 12i squared. Then you combine your imaginary parts and get negative 5i. Remember, right here, I squared is negative 1, so this is negative 1 times negative 12 is positive 12, plus 2 gives you 14. I got 2 times 3 is 6, minus 2i, minus 6i, plus 2i squared. Combine your imaginary parts, you get negative I, 8i. 1 squared is, I squared is negative 1, so I got negative 2, and 6 is 4, minus 8i. Multiplied something wrong when I did my notes. Sorry. All right, dividing complex numbers. Well, first I wanted to divide them, but you don't. You multiply by the conjugate of the denominator. Remember, the conjugate means you may change the middle term. So let's see if I can get this a little bigger. There we go. So I'm going to multiply by 1 plus I, top and bottom. So when the bottom multiplies, you get 1 plus times 1 is 1. The middle term drops out, and a negative I squared. The top, you get 3, and you have negative I. This is negative I, and positive 3i is 2i. And then you get minus I squared. And you have to clean it up. I squared is negative 1, and then it's negative, so it's positive 1. You get 4 plus 2i on top. This is negative 1, you're minus a negative 1, so it's plus 1 is 2. That you can simplify. You can pull a 2 out of all of them, and you get 2 plus I. Nifty stuff. Okay, same thing here. Multiply by the conjugate of the denominator. First thing I did, though, is rewrote it. So this is 1 plus I and 3 plus I, because it drives me crazy if it's not in the right order. Now multiply by its conjugate, 3 minus I, 3 minus I. The top is 3. You got 3i minus I is 2i plus I squared. The bottom, you get 3 times 3 is 9. The middle term drops out, and you get a negative I squared. When you clean it up, this is negative 1, so you get 2 plus 2i. And the bottom is 9 minus a negative 1, which is 10. You can pull a 2 out of all of those, and you get 1 plus I over 5. Alrighty? That was fun. All right, the fundamental theorem of algebra. It says every non-constant polynomial, in other words, y equals 6, doesn't count, has a 0 in the complex number system. There's some value. It can be complex means you have integers, you have rational, which are fractions, and you have irrational, which are square roots, and then you have complex, you have imaginary. Alrighty? And then the conjugate zero theorem says if a complex or irrational number is a 0 of a polynomial, so is its conjugate. So if 1 plus the square root of 7 is a root, then you know 1 minus the square root of 7 is a root. 3 plus 2i is a root, and 3 minus 2i is a root. All right. I love this. Write a quadratic equation that has a root of 1 plus or minus root 3. This is the way I always did it. I wrote it as the roots as factors. X minus the value, X minus the value, and then you foiled it. But I foiled it, which took forever. I love this. You move your parentheses. So instead of your parentheses being here, you move them to here, like this. And now this is the difference of squares. So this is a squared minus b squared. You FOIL this one, you square that one, and you got your answer. Here's another option. You use the sum of the roots and the product of the roots. If you add your irrational numbers together, this is equal to negative b over a. If you multiply them, this is equal to c over a. So a is 1, b is negative 2, and c is negative 2. And then you can write your equation. I thought this was an interesting option. Set x equal to one of the roots. X equals one of the roots. Then keep the irrational and non-real part by itself. So you move the 1 over here, and you square both sides. And you end up, which is kind of cool. Never tried that. But basically, that's what you're doing over here. Alrighty? So, write an equation of a polynomial in standard form with the given roots. All coefficients must be rational numbers. All right. Meaning they can be fractions, but they can't be imaginary or square roots. So first you turn these into factors. So it's x minus 4, x plus 1, x minus 2. Remember to always change the sign. Now you FOIL. I FOILed the first two and got x squared. I have minus 4 plus 1 is minus 3x minus 4. And then I have to multiply it by this. I just went ahead and FOILed the whole thing out. So I got x cubed minus 2x squared. Then I did this one. Got minus 3x squared plus 6x. Then I did these. Got negative 4x plus 8. Now combine like terms, and you end up with your function is equal to x cubed. Let's see, that's minus 5x squared plus 2x plus 8. Okay, that's not bad. This one, when it has a multiplicity of 2, it means write it twice. So you have x plus 2, x plus 2, and x minus 3. I'm going to let you do the math. When you get done, you should end up with x cubed plus x squared minus 8x minus 12. All right? So let's do one that's a little more complicated. Here's your factors. You have x minus 1, x minus 2 plus root 5, and x minus 2 minus root 5. I'm going to deal with these two first. I'm going to use the first method where you regroup them. I'm going to put these here like that. So when I work it, you get x minus 2 squared minus the square root of 5 squared. This is x squared minus 4x plus 4. This square root of 5 squared is 5, so that's minus 5. So now this is x squared minus 4x minus 1. And I'm going to multiply that times x minus 1. And when you're done FOILing, you get x cubed minus 5x squared plus 3x plus 1. You might want to stop the video, do it yourself, make sure I did it right, because I've been known to make mistakes. Okay, this one, same thing, you can do it twice. You have x minus 2 minus 3i, x minus 2 plus 3i, x minus 1 plus root 7, and x minus 1 minus root 7. Come back through and regroup them. I just love this. This is just fun. Okay. So now what do you have? You have x minus 2 squared minus 3i squared. And here you have x minus 1 squared minus square root of 7 squared. This is x squared minus 4x plus 4. This is 9 times negative 1, so this is plus 10. This is x squared minus 2x plus 1. This ends up being minus 7. So now you have x squared minus 4x plus 14 times x squared minus 2x minus 6. When you FOIL those out, I ended up with f of x is equal to x to the 4th minus 6x cubed plus 15x squared minus 2x minus 78. That's pretty sloppy. Sorry about that. Okay. Number 6, factor completely over the set of real numbers. Okay? Real numbers. That's going to means you can't have imaginary. All right? They told us 2 minus I is a 0. So let's do this again. It's x minus 2 minus I, x minus 2 plus I. Regroup. So I got x minus 2 squared minus I squared, x squared minus 4x plus 4. This ends up being plus 1, so you get x squared minus 4x plus 5. Now I have to do long division. X to the 4th minus 4x cubed. Make sure you copy your problem right. I make mistakes like that all the time. Now multiply to x squared to get to x to the 4th is an x squared. So this becomes x to the 4th minus 4x cubed plus 5x squared. You subtract, they'll go away, they go away. This becomes negative 7x squared plus 28x minus 35. You multiply by negative 7, and you get negative 7x squared plus 28x minus 35, and your remainder is 0. Okay? Now, I'm going to scroll down here to the bottom. So one of my factors is x squared minus 4x plus 5. The other one is x squared minus 7. Okay? That's factored over integers. If I want to factor it over real numbers, this is x squared minus 4x plus 5. This one is the difference of squares, so you have x minus root 7 and x plus root 7. Okay, that's over real numbers. Over complex numbers, you end up with x minus 2 minus I, x minus 2 plus I, x minus root 7, and x plus root 7. That's over the complex numbers. Okay, so if they ask you to factor it, this is over integers, this is over real numbers, this is over complex numbers. And they'll all get you back to this polynomial. All right? All right, last example. 1 0 of a polynomial is given. Find all the zeros. Since it's just an integer, I can do synthetic division, which is easiest. Remember to put down your coefficients. Put in a 0 if you're missing something. All right, we've got descending order, x cubed, x squared, x and the constant. Bring down the 1. 3 times 1 is 3. Add and you get 1. 3 times 1 is 3. Add and you get 1. 3 times 1 is 3. And you get 0. Thank goodness, because they told us it was a 0. Remember, these are the coefficients. So you have x squared plus x plus 1. That doesn't factor, so I'm going to use the quadratic formula to find my other zeros. So you have negative b plus or minus the square root of b squared minus 4ac over 2a, which is negative 1 plus or minus, this is negative 3, so you pull out the I. So there's 2 of them, and there's the other 0. Okay. This one, they told me I is a 0, so I know x minus I and x plus I are roots, or factors. If I square this, you get x squared plus 1. Now I have to do long division again. X squared plus 1, x to the 4th minus x cubed minus 5x squared minus x minus 6. You multiply by x squared, you get x to the 4th plus x squared. Subtract, you get negative x cubed minus 6x squared minus x. You multiply by x, negative x. And I'm running out of space. Hang on, I'm going to have to erase. So we have room to work. I hope you took notes on that. Darn it. Okay. So back to math. You get negative x cubed minus x. You subtract, you get negative 6x squared minus 6. You multiply by negative 6. Negative 6x squared minus 6, and you got 0. So they wanted me to find the 0, so I have plus or minus I, and now I have x squared minus x minus 6, which factors? Always check. X minus 3 and x plus 2. So you get x equals 3, x equals negative 2. So here's a root, and here's a root. And that's all there is to it. I love these little tricks up here. This is just way cool.